And welcome everyone to this keynote. I'm excited to have Hagit talking about hyperproperties. Today, Hagit is a professor at the Technion, and she holds numerous awards. For example, the Dijkstra Awards that she received 10 years ago. And yeah, I guess in the community, everyone knows her and is looking forward to hearing about hyperproperties when using concurrent objects. Stage is yours.
Okay, so I'll share my screen. Yes, this. Just organize the real estate on my. Do you see my cursor, by the way?
Yes.
No.
You do.
Yes.
Well, yeah.
You see it. Good.
Yes.
Yes.
Okay. Fine. Great. So this is talk about joint work with Konstantin and Jennifer Welsh. First of all, of course, I want to thank you for the opportunity to speak in SRDS and for tuning in, whether on Zoom or on YouTube. So let me start with a question, because I think this is always a good way to start the talk. And this is like, what do you think is the most significant concept in computer science, the most impactful, if you want? And you can put answers in the chat, but I here put some stuff that I'm sure some of you will say: Turing machines, risk architecture, machine learning, complexity classes, TCP/IP, object-oriented programming. You could go on and on and on with such answers. But to be honest, I have a different answer. None of these, basically. And I think my answer is the concept of abstraction, which I think in many ways hides or surpasses all these other concepts. So abstraction is basically our ability to encapsulate something that does a particular task within kind of a box, say what we expect of it, and then in some sense stop worrying about what's happening inside this box, what's happening under the hood. And in many ways, Turing machine is an abstraction of how computation is done. Risk architecture is an abstraction of how the actual, transistors and whatever do their jobs, gates, etc. Complexity classes is a way to say, I don't know what exactly happening when this program is running, but it's more or less behaving in this particular way. Of course, the communication stack, the networking stack, IP, etc., is one big abstraction in many layers, actually. And I think the abstraction has been one key reason that computer science has been very successful. Okay, because it allowed us to make progress in various dimensions, so to speak, planes, if you want, without worrying about what's happening in the other planes. So we can design new algorithms while our physicist friends are changing the way transistors and gates are implemented. Okay, and we can think about complexity classes without worrying about programming languages. Okay, so abstraction is a great idea. I think captures a lot of is a key for much of our success. And in the concrete, in the context of distributed and parallel programming, it's often presented in the following way. We have a program. And when writing the program, we assume the existence of an abstract object that does various things. And then actually we implement this abstract object in a way that depends on the specific communication system that we have, say, shared memory, message passing, synchronous, asynchronous, different kinds of primitives, different kinds of assumptions about failures, and so on and so forth. Okay, and we get better implementations or worse implementations, and so on. And a classical example goes back to Rampart is the register abstraction. So we write computer programs assuming that we have an atomic register. And then we can go on and say, Okay, but rather than getting a real atomic register through a shared memory system, we could, for example, replace this atomic register with a simulation or implementation of this register, for example, in a message passing system. So this is, of course, an example that is dear to my heart because it's the ABD implementation where we take the register abstraction, atomic register abstraction, and we implement or simulate it in a failure-prone message passing system. And the ABD algorithm is a very simple algorithm, and it works in an asynchronous message passing system under the assumption that at least the majority of the processes do not fail. So my next slide is basically the whole code of the algorithm. I think this is one of the reasons this has been a particularly successful algorithm is because it's really a simple idea. Okay, so let me walk you a little bit, remind you what's happening in ABD. And this is actually the so-called multi-writer version of ABD due to Lynch and Schwarzman. And in the multi-writer version of ABD, what we have is the operations that we support provide are a read and a write. And in order to write the value V, basically what we do is we replicate the value of the register across many servers. Okay? Each server keeps the latest value of the register as they know it, and they know it's the latest by associating a timestamp with each value. Okay? And now once you do that, the algorithms for the client operations are very simple. The write basically queries all the servers to get the latest timestamp, basically. I mean, they get the values, but they actually ignore the values and just take timestamps. Then it picks the largest timestamp it has received, and then increments it with 1, and then broadcasts an update with the new value and the new timestamp, and waits for a majority of acknowledgement. So again, I broadcast a query, get answers from a majority, picks the largest timestamp, broadcast the new value, and wait for an acknowledgement. So that's the write operation. And the read is actually almost exactly the same with one small change. So again, we broadcast a query, wait for replies from a majority of the servers, pick the value with the largest timestamp, and now we don't increment the timestamp. We just remember the value, and then we do what's called the write back of the new value to all the servers and wait for an acknowledgement from a majority. Okay, so that's the algorithm. I believe many of you are familiar with it. Okay, fine. So we have this this algorithm, and the nice thing is that it allows you to design algorithms for failure-prone message passing systems, assuming as if you have a register. So two, I think, nice examples are the way disk access, designed by Gaffney and Lamport, is first designed assuming a shared register, an atomic register, and then ported to a message passing system using the ABD implementation. And more recently, Garari et al. Used basically ABD to design a first cut version of an asset transfer protocol, which is like a key part of the Bitcoin protocol. Okay, so that's the ABD and its usage. Now, if we look at that, we need to ask ourselves, when we are doing this substitution, okay, when we are taking the program, designing, assuming the abstract object, the atomic register in our case, we think of as the specification. And then we replace the abstract object with what I would call the concrete object, the implementation, say message passing. Okay. And what we want to do is we want to say, okay, we wrote P, assuming spec, the abstract object, and now we substitute it with obj, the concrete implementation. And we proved properties of P when P is executed with spec. And now we want to say they continue to hold when we execute P with the object. Okay, so this is the substitution. If you know Liskov's famous Popple talk about the substitution principle. So we substitute something for another, and the properties we had for the program still hold. So what should be the relation between the abstract object and the concrete object in order that properties we proved for the program with spec will hold when we run the program with the concrete object. And the property, the relation that we want is a property called refinement, which I'll denote by less than or equal. So we say that the object refines the specification, the concrete object refines an abstract object spec, if and only for any program, P, the traces we can get when we execute P with the object, the concrete object, are a subset of the traces we get when we execute P with the specification, the abstract object. Okay, and when the abstract object, the specification, is a sequential object, we get probably the most prominent, the most important and famous instance of substitution, a concrete object for an abstract object, and this is linearizability due to Herlian. Okay. Now it's important that the property that we have is what's known as trace inclusion. Okay, the traces with the concrete object are a subset of the traces with the abstract object. So if a property is a property of traces, okay, for example, mutual exclusion is never violated. Okay, is a property of a trace, of an individual trace. So if you prove a particular property, a trace property, when executing P with spec, okay, so when we have some property that holds here, when we execute P with the abstract object, so you see my cursor. Okay, good. So when you see that, and when we have proved that the property, say mutual exclusion, holds when we execute P with the abstract object, then if we have trace inclusion, if we have refinement, then it will continue to hold when we execute P with the concrete object. So if you prove mutual exclusion when using an atomic register, it will hold when we'll substitute the atomic register with an ABD simulation of an atomic register. So if there are any questions, this is a good time to write them in the chat or somehow. Okay, so far so good, but as you can, so far so good. And one thing I want to talk for a few minutes now is how do you prove refinement? And basically there are two major ways to prove refinement in the context of linearizability in particular, and this is by showing a simulation. So basically what we show is that the concrete object, simulates the abstract object spec. Sorry. Okay, so we relate the states of the abstract object to the states of the concrete object to the states of the abstract object. Okay, so we show a simulation relation. We map basically each state of the concrete object to a state of the abstract object, and if we have this relation from this state of the concrete object, CS1, to a state of the abstract object, okay, we have a forward simulation if we can show that there's basically a state of the concrete object CS2 that is reachable from CS1, okay, so that there exists a state of the abstract object, okay, there exists a state of the AS2 of the abstract object that is reachable from AS1 and has the simulation relation to simulation mapping to CS2. Okay, so that's a forward simulation. So we go forward in time from CS forward to CS2, and then we have a way to go forward from AS to AS1 to AS2. Okay, so that's a forward simulation, and a forward simulation basically is a formal, grandiose way to say to capture proofs that are based on explicit linearization points. So basically, proofs in which you look at the implementation and you say, oh, when I do this, which could be in the process's code or somewhere else, or when this happens, I linearize the operation. This is where it actually happens. Okay, and it's typical, proofs like that are typical to universal constructions or various implementations using consensus objects or strong primitives like concurrent swap. So that's nice. But interestingly, not all implementations can be proved using forward simulations. And I didn't talk about this, but this is now a good time to tell you how, for example, ABD is the correctness of ABD, the linearizability proof of ABD goes. And the linearizability proof of ABD goes by looking at all the right operations, including some pending ones, okay, ordering them by their associated timestamps. Remember, each operation had a unique timestamp. And then you order the writes, and then you look at the reads and you stick them in the right place. So their semantics is preserved. And because we include some pending writes, okay, it's not like we go through the execution and there's a point we can say, oh, now the write happens. Now the write really happens. No, you just go and you just order based on what you have there. And such proofs are, so basically we find an after the fact relation based on the timestamp. And the formal way to capture some such proofs, such linearizations, is through a notion called backward simulation. So in backward simulation, we have again a concrete state 1 that can, from which we can reach a concrete state 2, and we have a simulation relation that relates the abstract state to the second abstract state to the second concrete state. And we argue that there is, an abstract state 1 that is in the simulation relation to the concrete state 1, and from which we can reach the abstract state 2. And a very nice result proved by Lynch and Van Brugger is that you can always prove linearizability through a combination of forward and backward simulation. And you may be familiar, some of you who are working on verification, you may be familiar with the notions of proving correctness through auxiliary variables. And basically forward simulation corresponds to history variables, while backward simulation corresponds to prophecy variables. And if you think about it, prophecies, basically we guess what the future will be, and then we kind of do the backward argument. So it's massive hand waving, but still I think it's a good intuition to carry. Okay. So I talked about abstraction, I talked about refinement, I talked about simulations as a way, forward and backward simulations as a way to prove refinement. And I talked about the fact that refinement preserves trace properties. And of course, the natural question to ask is everything a trace property? And as you can guess from the title of my talk, and if you attended Morris's talk yesterday, actually, I was kind of surprised to hear that, not everything can be captured, is preserved by refinement or linearizability. Not everything can be described as a trace property. And let me give you an example, an interesting example. I think that's, okay, so I want to go beyond trace properties, and I want to show you an example of basically a probabilistic termination argument. So this is a program that is distilled from a paper by Hatzilakos fluid to egg, and where we basically made it more succinct and reduced it to a very smallish, as small as possible program. So in this program, we have it's a program for 3 processes, P0, P1, and P2. What P1 and P0 and P1 do is basically, okay, we have 2 variables, R and C. And what P0 and P1 do is they do kind of a race on R to write their identifiers. So P0 writes 0 and P1 writes 1. And then after they finish, P0 goes home and P1 flips a coin and writes it in C. That's the code here. Okay, so each of them writes their index, their identifier into R. And if you are P1, you flip a coin and you write it into C. Okay, what P2 does is basically tries to observe the race. how the race was decided, so to speak. So P2 tries to read R twice and to catch two different values. Now this is an atomic register, so there's no guarantee that this will happen. Okay, but P2 tries to read R and see the two writes to R, to basically see two different values in R and in what order they happen. Okay, so that's what it does here. It reads R once, it reads R's a second time, and then it reads the coin flip. Okay, and now we have this complicated condition here, and it's hard to read it definitely now, quickly on the slides and all that, but what you should have in mind is the following thing. Basically, if P2 didn't manage to see two different values, this condition will always return true. Okay, so it's set up in a way that if for some reason P2 read R before anyone wrote it, or read one twice between the two writes, or read one after all the writes were completed, or read C before coin flip was written, or all these things, it's written in a way that no matter what happens, when all these things happen, it will return true. Okay? The only interesting case for this condition is where P2, for somehow, magically happened, it read two different values from R and then read the coin flip. Okay. And when this happens, P2 will return true if the value of the coin flip is equal to the last value read, so the second value read. Okay, so let's see an example. Sorry, let me go back. Sorry. Okay, so it will return true only if the value of the coin flip is the value of the second value read. Okay, and if the value of the coin flip is equal to the first value read, then it will return false. That's the way it's set up. And this setup, because the coin flip is fair and everything is atomic, ensures the following property, that P returns true with probability at least half if C and R are atomic registers. And to kind of see, it's not really the proof, but kind of the interesting case of the proof, look at these three processes. So they do the writes in some order. Here I have that P0 went first and then P1. And then P2 was successful in reading two different values. Okay. And then the coin was flipped. And basically, if the value of the coin was equal to the second one, then P2 will return true. Otherwise, it will return false. And in all other cases, it returns true. Okay. Now, the key for this property is the fact that when the coin is flipped, P1 already wrote its value. This is an atomic write. So this is either P0 already wrote its value. So the order is 0, 1, or P0 still didn't write its value, so the order is going to be P1, P0. But once the coin is flipped, the order between the two writes is already fixed, and it cannot be changed. And either we're lucky and it's the second, the value of the coin flip is the second value written or not, but that's set. Okay, this happens with probability half, and an adversary has no way to change the order of the writes after the coin is already flipped. So that's what happens if the registers are truly atomic registers. Now, what happens if we, instead of having R be an a truly atomic register, we actually replace R with an implementation, we simulate R using ABD. Okay. Now, the thing is that using ABD, we have the writes in flight, so to speak, and they are being executed. And it is possible that when P1 is flipping its coin, the write of P0 is still happening, and it's not an atomic thing. And once the adversary sees the value of the coin flip, it can mess with what's happening in the implementation. So either P0's write happens after P1's write, or vice versa, depending on the value of the coin. Here's a little bit, let me kind of try. And basically by doing so, the adversary, strong adversary that knows what's happened inside the processes, can make P2 always return false. Okay, here's kind of a hint how you do it. So basically, you have a preparation phase where P0 starts the query phase of its write. So basically, this phase of its write. P1 does its complete write and then flips a coin. And P2 starts its query phase of its first read. And then, depending on how on the result of the coin, so if it's a 0, for example, then what the adversary does, it schedules the write of P0 and the reads of P2 in a way that the second value returned by P2 is 1. And if the value of the coin flip is 1, then it's possible to schedule the write of P0 to be basically slower. So the first read of P2 gets 1 and the second one gets 0, and it returns false. So the condition here is not satisfied, and it returns false. So I'm stopping for a breath, and if there are any questions in the chat or okay, so basically this is an example where we have a program that has a positive probability, a constant probability of returning true, and we can make this that when you return true, you terminate or whatever, and if you return false, you basically don't terminate and so on. So you can make this into a really bad thing. And so it has a quantifiably good behavior when using atomic registers, but you can lose this behavior when implementing the registers through ADD. And this is an example of what's called hyper properties, or specifically hyper safety properties. And they include the two important classes. One is what we have seen, quantitative properties like termination with high probability, mean response time, and various probability distributions of events in the program. And another thing they include is security properties, policies like showing a property called non-interference, that you cannot learn about hidden high clearance values by observing what happens in low clearance values by low clearance users. So we were mostly interested in the first class, but the formality actually holds for both cases. Okay, so basically a hyperproperty is a property that you express as a set of traces. Okay, you cannot say that the probability of returning false is half or whatever by talking about an individual trace. You need to talk about many traces and say what happens, like half of these traces have, and half of these traces you terminate. Okay, you cannot express this property by looking at an individual trace by itself. And a hyper safety property are properties of sets of finite traces. So, okay, so let's go back. We have looked at refinement. We've shown that refinement preserves trace properties. And as you can guess, refinement does not preserve hyperproperties. Okay, and it's actually a well-known thing from formal methods from verification, already going back to 1994. So it's not a big surprise in retrospect that in 2011, Golub, Hayam, and Woffel discovered that linearizability does not preserve probability distributions under stronger or weak adversaries. So basically, they gave specific examples similar to the example I've shown you, but actually for snapshots. Okay, so hyperproperties refinement does not preserve hyperproperties. So what does preserve hyperproperties? And Golub and Hayam shown that strong linearizability, which is a variant, a restriction, a strengthening of linearizability, where linearization points do not depend on the future, it preserves probability distributions under strong adversaries. So in earlier work with Konstantin in this 2019, we have basically extended strong linearizability to the notion of strong refinement, which I'll describe with less than or equal with S for strong. And that's the definition, supposed to remind you of the definition of refinement. But what we do is we introduce into the definition explicitly the scheduler, okay, the way we're scheduling events of the concrete and the abstract object. So basically a concrete object is a strong refinement of an abstract object spec, if and only for every program. So this was like in like in refinement, and for every deterministic scheduler S1 of the program with a concrete object, we can find a deterministic scheduler S2 of the let's see, sorry, Wojciech, did I forget Philip? So I can find a deterministic scheduler S2 of P and with the abstract object spec, such that the traces, when running with the deterministic scheduler and the concrete object, are equal, exactly equal to the traces when we run with the abstract object. So of course, once they're equal, it's kind of almost obvious that you'll be preserving hyperproperties, okay? So just to say what the deterministic scheduler is, it captures a strong adversary and basically chooses who's the next thread or process that will execute a step based on the prefix. It does assume that the objects we work with are deterministic. And basically, we say that phi, basically think of phi as a program with a concrete, a program running with an object satisfies a hypersafety property if and only for any deterministic scheduler, its traces are included, are members in H. And the theorem, again, it's rather obvious once we have the right, we set the definitions correctly, that if a concrete object is a strong refinement of an abstract object, then for any program P, if it satisfies a hyperproperty with spec, then it satisfies the same hyperproperty with the object, with the implementation. So basically, if we satisfy strong refinement, we can ensure that hyperproperties are preserved. Okay, a nice thing once you have this definition, and this is why I dragged you through the notions of forward and backward simulation, is that once you have this formal definition, you can show that strong refinement holds if and only if we have a forward simulation. Okay. One direction is rather easy. So if we prove that an implementation refines a specification through forward simulation, then basically the forward simulation can help us carry the schedulers of the concrete object into schedulers for the abstract object. So it's actually rather obvious, and it's more words than they deserves. The interesting direction is actually the converse. So if something is a strong refinement, then it can be proved through a forward simulation. And the way you do it is you pick, note that what we have is that the property, the stronger refinement should hold for any program and any deterministic scheduler. So we pick a particular program and a particular scheduler that basically determinize the future. So we basically store all possible continuations, all possible futures into a state of the program. And then we use this, in some sense, kind of a future variable, a prophecy variable, in order to pick define the forward simulation. So that's a technical thing. It's not that complicated, but it's definitely the hard part of this result. Now, the nice thing about equivalence to to forward simulations is that it allows us easily to show a compositionality results, actually. Okay, and it's both what I would call horizontal composition and what I like to think of as vertical composition. So horizontal composition is what is known as locality for linearizability. So basically, if we have that a concrete object 1 is a strong refinement of an abstract object spec 2, and another implementation is a strong refinement of another abstract object, then you can basically run the two objects together, and there are strong refinement, of the two specification. Yes, Borzu.
Is it okay if I ask a question here?
Yes.
Okay. So hyper safety is closed under refinement. So if you do just traditional refinement, it preserves hyper safety, but it doesn't preserve a requirement such as linearizability, because linearizability is not hyper safety. But in the previous slide, I now forgot that whether you proved that strong refinement preserves hyper safety or it preserves another class of hyperproperties.
It preserves hyper safety.
But even normal refinement preserves hyper safety.
I don't think so, unless what we think about hyper safety are different things. So
that might be the case. Yeah.
Okay, so I might be not particularly precise on these. Okay.
So let me just add that, if the quantification over executions is universal, so for instance, you are quantifying over every pair of traces or every 3 traces or 4 traces.
Okay.
Compared to, if your quantification has some alternation of universal and existential, even if the inner behavior is safety, that requirement is not hyper safety. So for instance, linearizability is not hyper safety, although the bounded alignment of the traces with respect to linearization points is, you can look at it as a safety thing. But since it is quantifying over the existence of a trace or a linearized trace in the sequential object, it's not still hyper safety. But I guess you are right that maybe we are looking at different definitions here.
So I think you think about linearizability as a property, and I think about linearizability as a relation. And maybe
I agree with you. I totally agree with you.
So let's, I think that's an interesting observation, and let me think about it, and let's talk about it offline.
Sure, yeah.
Okay, so this property is well known for linearizability, that you can implement separate objects and then have separate linearizable implementations and then put them together, and they are still linearizable together. Proving this property for strong linearizability took quite some work from Golub et al. In the original paper. I see Wojciech is here, but it actually follows from the equivalence to forward simulation quite immediately. Okay, because they compose. I mean, if you get 2 forward simulations, then together they are forward simulation. And another property that's hard to do when you work directly with the definition is what I will call, formally is called parameterized objects. I prefer to think about this as hierarchical composition. So imagine that we implement, we have a strong refinement of some specification using a concrete object, and this concrete object uses inside some abstract object spec 1. And then we implement spec 1 in some way. And then we plug this implementation within the other implementation. Okay, and if all these implementations are strong refinements, then plugging in the internal implementation still leaves us with a strong refinement. So think, for example, that we're implementing multi-writer snapshots using multi-writer registers. And then we implement the multi-writer registers using single-writer registers. Okay, and all these are strong compositions, strong refinement, or strongly linearizable implementations. And then when we put everything together, we get immediately a strongly linearizable implementation of snapshots from single writer registers. Okay, and again, this is not obvious. There was a direct proof of that, but it takes work. Once you work with forward simulations, it's rather easy to derive this property. Okay, so if we had implementations of snapshots from strongly linearizable implementation of snapshots, or if we had strongly linearizable implementations of multi-writer registers, everything was nice. But that's a good time to ask which objects have strongly linearizable implementations. And the answer is, very few, not very few, but very few in the domain that I like to call sub-consensus. Okay, so which objects? That's basically, we know if we have a forward simulation, then it's a strongly linearizable implementation. Great. So I mentioned before that proofs, if the implementation is proved correct using explicit linearization points, then it's strongly linearizable. So universal implementations, many implementations using compare and swap, etc., are strongly linearizable. But once you go to the domain where consensus, we implement objects in the world where consensus cannot be solved, then things become murky, and usually we have negative results. So the algorithms in Golub et al., they've shown that the original snapshot algorithm is not strongly linearizable. An interesting implementation of stacks in Common2 is not strongly linearizable. This is something Konstantin and I have shown. And then later, it was shown by Helmy, Hayam, and Woffel that snapshots, multi-writer registers, and other objects have no weight-free strongly linearizable shared memory implementations, and in some cases also no lock-free strongly linearizable implementations, and everything is pretty bleak. And in fact, you may ask, so I've shown you that specifically ABD is not strongly linearizable. ABD is not strongly linearizable because it wasn't preserving the termination probability in the program that I call W. So because it did not preserve, the counterexample that I've shown you shows that ADD specifically is not strongly linearizable. But maybe, maybe somebody smarter can find another strongly linearizable implementation of a register in a failure-prone message passing system. And the answer is negative. So this is a paper we have in upcoming ISC. And basically, we show that there is no strongly linearizable ABD implementation of a register in a failure-prone message passing system. And the way we do it is by reduction. Okay, so given a strongly linearizable message passing implementation of a multi-writer, multi-reader register for n processes and some number of failures that could be much, much smaller than the number of processes. Okay, we get from it, so this is the implementation that we have, we can obtain from it a strongly linearizable shared memory implementation of a multi-writer, multi-reader register that uses only single-writer, multi-reader registers, and it works with F+1 processes and F failures, so it's basically weight-free. And F is the same F as we had here. Okay, so we have some number of failures, could be very small. So for example, this could be even for 2 F equal 2. Okay, so we have a system, a message passing system with many, many processes. Okay, and it could be very large, and we'll simulate it with a system that has 3 processes, for example. And the reason I focus on 3 is because the result of Helmy et al. Shows that you cannot get a multi-writer, multi-reader register from single-writer, multi-reader register, and this holds even for 3 processes when we have 2 writers and 1 reader. Okay, so we do a reduction to the message shared memory implementation, which we know is impossible. Now, it's very important, something that I glossed over, is that the reduction, the simulation that we have, that we get, the relation is a strong refinement. So the whole thing will remain a strongly linearizable implementation. And the way we do it is, this is like a one-slide description of the simulation. I really would like to encourage you to watch, to attend the talk at DISC for more details. So basically what we do is, like in ABD, we think that we have separate client threads that handle the read and write invocations and responses. And we have the server threads that maintain state and respond to clients. Okay, so these are the client's threads, and these are the server threads. And then what we do is we statically assign the shared memory processes to client threads. So each shared memory process is responsible for, like, owns one client thread. So we have, say, 3 shared memory processes that are mapped statically to 3 clients. But servers, we have many, many more of these. And as you know, ABD relied on the fact that we had more than the number of possible failures. So N should be at least twice 2f+1. So to simulate the server threads, we collaboratively, the shared memory threads collaboratively simulate the server threads. And we do this through an adaptation of the Borofsky-Gaffney simulation. And I'm sure many of you don't know the Borofsky-Gaffney simulation. So let me tell you that basically what you do is you kind of reach agreement, the simulating threads, the shared memory threads, processes, basically reach agreement on each and every step of each server thread. And they do it using something called safe agreement. And the magic of the BG simulation is that we do agreement in a world where agreement with consensus is not solvable. So we do it deterministically and without blocking. So what happens? The thing is that the safe agreement may block if one of the simulating processes, shared memory processes, fail. But in this case, only this simulated server blocks. The other simulating processes make progress, or can make progress on their own with the other server threads. So if any failure of the shared memory threads, if there is a failure of a shared memory process, it translates to a failure of a single message passing server thread. Now, the details are, of course, not at all simple, and definitely translating the concepts of shared memory. So BG simulation originally was done between shared memory algorithms. And here we take a message passing algorithm and simulate it in shared memory. Okay, so in some sense, this is an inverse or converse of ABD. ABD takes a shared memory algorithm and runs it in message passing. This takes a message passing algorithm and runs it in shared memory. And another thing you should note is that because there's agreement on the server threads, the server steps, this ensures a strong refinement. Okay, the fact that we do each step with an agreement, somewhat blocking agreement, then this is the core of arguing that this is a strong refinement. So again, the details are not obvious, but I think the key ideas are on this slide. Okay. So this is like bad news all the way. No snapshots, no multi-writer registers, no ABD, etc. Ways what to do. So one thing is to forego abstraction, basically, and basically plug something like ABD and do explicit argument about correctness. But that's obviously not what I want to encourage. Other things you could do is have implementations that are not weight-free and then deal with it somehow, or that are working for a constant or fixed bounded number of iterations or invocations and things like that. So there are solutions like that. Here I want to propose something that we've been toying with in recent months, And it takes its inspiration from the techniques of program obfuscation and oblivious realms. So I know this is kind of outside our usual scope, but I think these are really nice techniques, and I think we can learn from them. So what's indistinguishable obfuscation? This is like quite a mouthful, but I'll manage. So basically, this is a way to take a program that does something and perturb it, morph it in some way, that it still has the same functionality, hence the indistinguishable, but it's obfuscated in the sense that an external observer doesn't know what's happening inside this program except for its input-output relation. So you could execute a program with particular inputs and get the output, so you know something about the input-output, but you don't know what's happening inside the program. So you can see why it will be very useful in like cloud and virtualization, and you have it, crypto settings. Basically, it's kind of a special case of that is something called oblivious realm, which I think is easier to understand. So oblivious realm, all I want to hide is not what's happening in the program, but the precise memory access pattern of my program. So for example, I want to read A, B, and C. Okay, so what you do in ORAMs, this is like the naive ORAM and the very inefficient one, you pick random locations, and then you access all these locations and you hide the ABC inside these accesses. So I access X1, B, X2, X3, whatever, C, etc., and then I access A, and then X5 and whatever. Okay, and the external observer sees me accessing this 8 location or 9 location or whatever, and then I just get them and I pick the ones that I really cared about. Okay, so basically this is like hiding a needle in a haystack. I do lots of things, and the adversary doesn't know what is the real thing that I'm going to take. So we take the execution. So what we want to do is kind of borrowing this idea. We want to take the computation, the way the concrete object is operating. We want to perturb this implementation somewhat in a way that the adversary is blunted, loses its extra power, while the functionality of the object is kept indistinguishable, is not changed. So how do you do that? It's kind of magic. So the idea is always, like in ORAM and in IO, is to use randomization. So because the program that is using these objects is going to be random anyway, I'm going to embrace randomization and introduce randomization inside the implementation itself. So here's an example for ABD. So we have a program, P, that is using an atomic register. And we have in mind, we are going to plug ABD, replace the atomic register with an ABD. Now, instead of just running ABD, I'm going to run ABD several times. Okay, basically I run the query phase of ABD several times. So if I read, and I read, and I read, and then I flip a coin. Okay, I flip a multi-sided coin. And I pick one of the values that I got in the queries that I executed. Okay, so say, for example, I executed m+1 instances of ABD. I flip an m+1 sided coin, and one of these values is the value I'm going to return, and then I do the write back for this value. Now, nothing bad. I mean, obviously, the functionality remained the same. Okay, you can think that I wasted some work, but this is still, any of these is an okay value to return. But the thing is that if the program P had flipped only m coins, had inside P there are only m coin flips, then at least one of these instances, one of these invocations of ABD does not overlap any coin flip. Okay, just by counting, okay, pigeonhole counting. Okay, and this invocation is as if there were no coins. There was basically, it was truly atomic. Okay. Now, if I was lucky enough to pick this particular one, then I won against the adversary. Okay. So I'm not happy and free because I wasted more work, and not always I don't succeed always. But with some probability I succeed, and if I'm lucky, I mean, if I balance the numbers correctly, the extra work is not huge. And this is, I think, the best theorem we can now prove so far. So if we have a program P that has m coin flips, then repeating ABD m+1 times, if some property phi holds with probability that is with a non-zero probability, then it holds with ABD m+1 with non-zero probability. Okay, and specifically in the example, this will be my last real slide, by the way. Okay, so my last real slide is blunting basically if the program flips just one coin, which is the case for the program W that I've shown you before, just has one coin flip. Okay, so basically what we have is we have this, the right does a broadcast a query and get the largest timestamp, and then basically does the same thing again, get the largest timestamp, and then picks one of them with probability half, and then picks this timestamp and send it. And same for a read, you do a query, you get the largest, the pair with the largest timestamp, you do it again, that you get the pair with the largest timestamp, and you pick one of them with probability half. And basically it can be shown that when you run this ABD squared with the program W that I've shown you before, you can show that you cannot prove that P2 returns true with probability half as before, but with probability 3/8, which is less, not as good, but still something you can cash on. So obviously there are many things to do here. We are just really getting started. As I said before, we only prove a qualitative property that if the probability is larger than 0, then it's also larger than 0 with ABD m to the power m+1. Again, we can do the blunting with other concrete objects, basically keep the behavior of the object indistinguishable to the program while not letting the adversary have extra power. And we can do it for snapshots and for multi-writer registers and for multi-reader registers, basically all the bad things that we know. Sorry. So finally, zooming out, my last slide. I think looking at what I've shown you is we have this picture that we have a program that is using an abstract object, and then you replace it with a concrete object. You want to ask what is the relation, what relation should hold between the abstract object and the concrete object, and then you think about the property that you are trying to preserve. And basically, you can play with each of these elements separately and think about them. So, for example, as I already mentioned, you could have other relations between the abstract and the concrete object. So, for example, Hatzilakos et al. Presented the notion of right-strong linearizability, which is sometimes implementable, but not always, and has its limitations, and it's helpful sometimes, not always, etc. So it's a nice concept. You could talk about properties that are not hypersafety properties that deal with infinite traces. So there's a recent brief announcement at DISC. And I already mentioned quantitative blunting, so being more, having a quantitative argument about phi, basically how the guarantee we have with the abstract object is translated to the guarantee we have with the concrete object. And finally, we don't need to think just about sequential specifications. They could be transaction systems. The specification could be cryptographic protocols. Actually, they could be distributed ledgers, if we'll look at Morse talk from yesterday, and so on and so forth. So each of these aspects, I think, could be a wonderful place to play. So I'm done.
Thanks a lot, Hagit. That has been great. Very nice insights. Do we have questions in the audience?
Roberto.
Yes.
Roberto. Yeah.
Thanks for the presentation, Hagit. So I'm not sure I was able to follow everything and all the details, but recently we have been looking into the this new networking technology, RDMA, the remote direct memory access, which basically allows you to access memory from another machine. And so my question was related to the programming model. You've been looking into message passing and or shared memory. Recent papers have trying to like bridge this gap and having a little bit of both. We are trying to, we wrote a paper recently where we are trying to increase the power of this hybrid model, let me call it this way, by means of adding atomic operations. And we have looked into ABD. In our paper, there is an implementation of ABD using RDMA and using this model, this new model that we provide. I was wondering, the characteristics that we're more passionate about, and we think about innovating and we think about exploring, is this the new failure model. So process not just crash or behave arbitrarily, but you can consider like the memory is always available, but the process can crash. So you can always access the state. So I was wondering if what's your take on these new failure models and how they will affect the kind of considerations you have made here or looking forward?
So actually, I worked on these mixed models, not with RDMA, where the processes that share memory use just reads and writes for it. And actually, I think it's actually what got me back to this was the fact that actually the simulations are not strongly linearizable because they are kind of a special case of ABD. If you have a concurrent swap or stronger synchronization inside the cluster, the shared memory parts, there's a possibility that you could be more, that you could be strongly linearizable, maybe definitely within each cluster, but I think across clusters, things might be problematic. Though again, you are welcome to try blunting as well. So it's a fairly flexible and adaptive, agile is probably a good word for that. It's a fairly agile approach.
Interesting. Thanks. Yeah. We were thinking of what if the cast doesn't come back? So it will succeed. What if the cast doesn't come back to you because there is a failure? Right, because there is a failure where again you can still access the value, but the cast might not return. Or
so Wojciech, I don't know if he's still here, but Wojciech has studied the power of CAS with persistent memory, where a failure may occur. And if I remember correctly, the power deteriorates. And if it deteriorates, my suspicion, it will be hard to do it strongly linearizable. Okay, that's my, if I need to place bets, if you don't have good consensus power, you have trouble with strong linearizability. I still don't have a theorem for that, but if we would do betting, that's where I would place my money.
Awesome. Thanks, Hagit.
Do we have other questions? Okay, then I have one. So I'm working on this. What was your main motivation to actually get started?
So the original paper with Konstantin was because I really liked the original strong linearizability paper, but I always felt like they were too close to where we were, like a traditional distributed computing view of this. And I always felt that there must be insights from the formal methods community that could help us understand strong linearizability better. And then bumped into Konstantin in some Dutch tool, and we started talking about it. So that's how we ended up with the first paper. The paper, the blunting paper, was because we felt like that this, you know, there are all these negative answers. And one of them indeed was that we found that ABD is not strongly linearizable, and then we worked on proving that it's not, and so on and so forth. And I felt that this is, you know, there might be a way to get around this, to not take the implementations as is, but play with them and then plug them in. Okay, so it's probably not a good enough answer.
No, totally. I was just curious, and it's always nice to see how people get started with new problems. So one last question.
So do you have any ideas whether this can be efficiently implemented for verification?
Short answer is no, obviously. No, probably your guess is better than mine, to be honest.
So, I mean, the reason I'm asking you is, you know, we have our algorithms for verification of hyperproperties, but I want to see if there are, you know, other mindsets that could result in better verification algorithms. So I know from speaking from with my what I call verification friends like Noam Rinetsky and such, that if you have explicit linearization points, then verification is easy. Yes.
So in some sense, the fact that strong linearizability holds only if you have forward simulations means that if you don't have an easy proof, then probably what you have is not a strongly linearizable implementation. So I don't know how you can turn this into a formal result, but again, my sense is that if something is strongly linearizable, it should have a relatively easy, efficient proof. So there aren't many of these creatures, but when they are simple.
Yeah, very, very interesting. And I would love to talk to you.
But I could be wrong, by the way. I mean, just
no,
Jennifer is here. She knows I can hold 2 or 3 opinions at the same time. So
no, I think your intuition is perfect. I would love to talk to you and Jennifer and Konstantin about this at some point.
Sure.
We have done some work on verification of linearizability. I mean, that's for hyperproperties, but we had a case study for the snark algorithm, which we could find the bugs in both bugs in the algorithm with model checking. So would love to talk to you at some point.
Sure.
Yeah.
Okay then. Well, thanks again, Hagit. That has been really great, and thanks for all the questions. And the next session will be the best paper finalists. So